In this video, we're going to go over the KutaSoftware Infinite Pre-Calculus free worksheet, area under a curve using limits of sums. Before we jump into the worksheet though, let's go over 3 rules and 2 formulas that we're going to utilize in most of these problems. First, we'll go over the rules. One rule says that if you have the sum from k equals 1 to n of a constant c, then that is always going to be equal to c times n. Another rule states that if you have the sum from k equal 1 to n of c times some function in the form of a sub k, you'll be able to pull out that constant in the front of the summation, and you can have c times the summation from k equals 1 to n of that a sub k. And then lastly, there's another rule when you're going from k equals 1 to n of sum a sub k plus b sub k. That is the same as taking the summation of k equals 1 to n of a sub k and then adding that to the summation of k equals 1 to n of b sub k. Same goes for subtraction. So if you're subtracting those terms, you take the summation of one term and you subtract it from the summation of the other term. So essentially you can split up those summations. So those are the 3 rules. Now let's go over the formulas. One formula states that the summation from k equals 1 to n of k, so k to the first, so we're looking at the variable with the degree of 1, then that is equal to n times n plus 1 all over 2. And the last formula is the summation from k equals 1 to n of k squared, so with a degree of 2. That's going to be equal to n times n plus 1 times 2n plus 1 all over 6. Let's jump into number 1 and start utilizing these rules and formulas. In numbers 1 through 4, we're to evaluate each sum. And looking at number 1, we're evaluating the sum of 48k from k equals 1 to n. However, you can see that 48, so I'm going to rewrite this as 48 times the summation from k equals 1 to n of k. So in that step, I use that second rule saying that we could pull our out in front of our summation. But now I'm left with 48 times the summation of k from k equals 1 to n. But we have a formula for that summation, and that's n times n plus 1 over 2. So I'm just going to substitute that in. So now I'll have 48 times n plus 1 over 2. Now right away I can simplify because 48 divided by 2 is going to be 24. So I'll have 24 times the numerator, n times n plus 1. So now I'm going to be distributing this 24n to both n and 1. And that will give me 24n squared plus 24n, because 24n times n is 24n squared, and 24n times 1 is 24n. And that's my solution in number 1. Let's look at number 2. In number 2, I'll start by pulling out in front. So I'll have 16 times the sum of k squared from k equals 1 to n. Now you can see that the sum of k squared is a formula. That is equal to n times n plus 1 times 2n plus 1 over 6. So now I'll have 16 times n plus 1 times 2n plus 1 all over 6. So I'll rewrite this foiling or expanding my 2 binomials. So I'll have 16n times n times 2n is 2n squared plus n times 1 is 1n plus 1 times 2n is 2n, and then I'm adding that to 1 times 1, which is 1, and that's all over 6. And now I'll distribute my 16n. So 16n times 2n squared is 32n cubed, and I'm adding that to 16n times n plus 2n, which gives me 3n. So 16n times 3n is 48n squared, and then I'm adding that to 16n times 1, which is 16n. And I was able to combine n and 2n because they're like terms. And that's all over 6. So my last step, I'm just going to split up this fraction and simplify. So I'll have 32n cubed all over 6 plus 48n squared all over 6 plus 16n all over 6. Both 32 and 6 are divisible by 2, so that's going to be 16 times n cubed over 3, dividing both the numerator and denominator by 2, and I'm adding that to 48 divided by 6 is 8, so that's 8n squared, plus 16 and 6 are both divisible by 2, so dividing both the numerator and denominator by 2, I'll get 8n over 3. So 16n cubed over 3 plus 8n squared plus 8n over 3 is my solution in number 2. Now moving on to number 3, remember we can split up this summation because the terms are added together. So I'll do the summation of k equals 1 to n of 36k plus the sum from k equals 1 to n of 6. Now in this first term I can pull out 36, so I'll have 36 times the sum of k equals 1 to n of k, and then this second one, this is the summation of a constant, which we know is going to be that constant times n. So this is equal to 6n. And that was because of the first rule I explained. Also remember that the sum of k from k equals 1 to n is equal to n times n plus 1 over 2. So I'll have 36 times n plus 1 all over 2 plus 6n. 36 divided by 2 is 18. So I'll have 18 times n plus 1 plus 6n. So now I'll distribute my 18n to my n and 1, and that will give me 18n squared plus 18n plus 6n, because 18n times n is 18n squared, and 18n times 1 is 18n, but now I have two like terms that I can combine. So that will give me 18n squared plus 24n. That is my solution in number 3. And lastly, in this section, number 4. Again, I can split up these terms. So I'll do the sum of k from k equals 1 to n plus the sum of 2 from k equals 1 to n. Now this is our formula, which is n times n plus 1 over 2, and we're going to add that to, taking the sum of the constant, that's going to be 2 times n, the constant times n. So what I'm going to do now, in order to add these two terms together, I'm going to put them over a common denominator. And as I put them over a common denominator, I'm also going to distribute my n. So I'll have n squared plus n all over 2, and that's going to be plus multiplying 2n by 2 over 2, which is essentially 1. That's going to be 4n over 2. Because 4 divided by 2 is 2, and 2 times n is 2n. Now I'll add those together to get n squared plus n plus 4n is 5n, and that's all over 2. And now I'll split this fraction back up. So I'll have n squared over 2 plus 5n over 2. That's my solution in number 4. Now on to my next 4 problems, numbers 5 through 8. In numbers 5 through 8, we're taking these summations a step further and evaluating the limit of each. So the same rules will still apply, and as well as the same formulas. So I'll have the limit from n to infinity of, I'll pull out So that's 12 over n squared times the summation from k equals 1 to n of k. Remember, the summation was a formula, so now I'll have the limit of 12 over n squared times n plus 1 over 2 as n approaches infinity. So let's do a little bit of simplification. 12 divided by 2 will give me 6. So I'll have the limit as n approaches infinity of 6 times n plus 1 all over n squared. Continuing my work, I'll distribute that 6n. 6n will get multiplied to n and multiplied by 1. So I'm still using the limit as n approaches infinity of 6n times n is 6n squared plus 6n times 1 is 6n, and that's all over n squared. Now I'm going to break up this fraction. So I'll have the limit as n approaches infinity of 6n squared over n squared plus 6n over n squared. So you can see my n squared will cancel out in my first term, so I'll have the limit as n approaches infinity of 6 plus 6n divided by n squared is going to be 6 over n, because my n in my numerator will cancel out one of my n's in my denominator. Now look, we're finding the limit as n approaches infinity. So if you remember our limits at infinity worksheet, or some of the limits at infinity tricks, as n approaches infinity, 6 over n is going to go to 0. Therefore, the limit as n approaches infinity would be 6, and then essentially plus 0, which is 6. So 6 is our solution in number 5. Now in number 6, we're going to do the same thing. This problem is just a little more in depth. And to speed up the notation, as opposed to writing the sum of k equals 1 to n, because this is the same, k equals 1 to n, for the rest of these problems, I'm just going to write this as the summation. But understand that it is still from k equals 1 to n. I'm just going to write it this way to speed things up. So now we have the limit as n approaches infinity of, I'm going to split these summations up. So I'm going to have the summation of 2 over n plus the summation of k squared over n cubed. Now right away, the summation of 2 over n is my constant, that's going to equal 2 over n times n. Because remember, the summation of a constant is that constant times n. And this is all as the limit of n approaches infinity. And for my second term, I'll pull out a 1 over n cubed and still have the summation of k squared, which we know is our formula. Now in the first term, my n's will cancel out because 2 times n over n is 2. So I'll have the limit as n approaches infinity of 2 plus 1 over n cubed times, remembering our formula, that's going to be n times n plus 1 times 2n plus 1 all over 6. So now I'm going to FOIL or expand my binomials, first, outside, inside, last. And because my numerator is multiplied by 1, I'm not changing the value of my numerator, but I'll go ahead and multiply out my denominator. So I'll have the limit as n approaches infinity of 2 plus n times 2n is 2n squared plus n times 1 is n plus 1 times 2n is 2n. However, I'm going to combine these terms because n plus 2n equals 3n. And that's going to be added to 1 times 1, which is 1. And this is all over n cubed times 6, or 6n cubed. Now continuing my work, I'm going to have the limit as n approaches infinity of 2 plus distributing that n to 2n squared, 3n, and 1. That will be 2n cubed plus 3n squared plus n all over 6n cubed. Now I'm going to split up that fraction to simplify. So I'll have the limit as n approaches infinity of, and I'm doing the limit of this entire term. So if you need to, include those parentheses. 2 plus 2n cubed over 6n cubed plus 3n squared over 6n cubed plus n over 6n cubed. Simplifying these fractions, 2n cubed over 6n cubed, my n cubes will cancel out, so I'll have the limit as n approaches infinity of 2 plus 2 over 6 plus 3n squared over 6n cubed. My n squared will cancel out to leave me with 1n in the denominator, and 3 over 6 is the same as 1 over 2. So I'll have 1 over 2n plus n over 6n cubed. My n will cancel out, and I'll be left with n squared in the denominator. So that's 1 over 6n squared. Now as n approaches infinity, 1 over 2n approaches 0, and 1 over 6n squared approaches 0. So I'm only looking at 2 plus 2 over 6, which is a constant. So 2 plus 2 over 6, I'm going to write this over the same denominator. So 2 will become 12 over 6, and I'll add that to 2 over 6, which equals 14 over 6, and both 14 and 6 are divisible by 2, so that will give me 7 over 3, which is approximately 2.3, and that's my solution for number 6. Let's move on to number 7. In number 7, I'll split up this summation at the start. So I'll have the limit as n approaches infinity of the sum of 6 over n plus the summation of 16k squared over n cubed. Now the limit as n approaches infinity of the summation of a constant is going to be 6 over n times n, and then I'm going to be adding that to, pulling out 16 over n cubed, the summation of k squared. So now I'll have the limit as n approaches infinity of 6 times n over n, my n's will cancel out, so that will be 6 plus 16 over n cubed times the formula for k squared. However, because this is just the summation of k squared, I'm going to go back up and use the expanded form of that formula, which we worked out in number 6. Here we're looking at the summation of k squared, which here is the formula, and then when we expanded out that numerator, it was 2n cubed plus 3n squared plus n over 6. Because that n cubed was the constant that I pulled out that got multiplied to the denominator, this is just over 6. So 2n cubed plus 3n squared plus n over 6. That is the expanded form of that formula. So again, that was 2n cubed plus 3n squared plus n all over 6. Now I'm going to multiply my numerators together, distributing the 16 to each of my terms, and my denominators together. So I'll have the limit as n approaches infinity of 6 plus 16 times 2 will be 32, so that will be 32n cubed plus 16 times 3 is 48, so 48n squared, plus 16 times n is 16n, and that's all over n cubed times 6, or 6n cubed. Now I'll split up that fraction to help me simplify. So I'll have the limit as n approaches infinity of 6 plus 32n cubed over 6n cubed plus 48n squared over 6n cubed plus 16n over 6n cubed. Continuing my work, I'll have the limit as n approaches infinity of 6 plus, simplifying, n cubed divided by n cubed is 1, so I'll have 32 over 6, and I don't even need to simplify these last two terms, because let's look. Remembering the limits at infinity, if the degree of the numerator is smaller than the degree of the denominator, we are approaching 0 as n goes to infinity. So for this, 2 is less than 3, so as n approaches infinity, this is approaching 0, and we have n to the first, and n cubed, and 1 is less than 3, so the highest degree in the numerator is less than the highest degree in the denominator, therefore this is also approaching 0 as n approaches infinity. So we just have the limit of 6 plus 32 over 6, which n is not even involved, therefore it's just a constant. 6 plus 32 over 6. However, I'm going to simplify this. Both 32 and 6 are divisible by 2, so I'll have 6 plus 16 over 3, and then I'm going to combine using a common denominator. So in order to get 6 in terms of 3, I'll need to multiply by 3 over 3, so that will be 18 over 3 plus 16 thirds, because 18 divided by 3 is indeed 6. And 18 plus 16 equals 34. So we have 34 over 3, which rounds to 11 and a third, or 11.3 repeating. That is our solution for number 7. And then lastly, for this set of directions, number 8. Again, I'm going to need to split up these summations. So I'll have the limit as n approaches infinity of the summation of 12 over n plus the summation of 8k squared over n cubed. And this is very similar to number 7. My first summation is the summation of a constant, so that's going to be 12 over n times n, and then I can pull out 8 over n cubed to get the summation of k squared. And remember, we're taking the limit of this as n approaches infinity. So simplifying, n will cancel out with n, because n divided by n is 1. So I'll have the limit as n approaches infinity of 12 plus 8 over n cubed, and that's going to be multiplied by, again, I'm going to use the expanded version of this formula, which, if we need to remember, was 2n cubed plus 3n squared plus n over 6. So again, that's 2n cubed plus 3n squared plus n all over 6. Now I'll multiply my numerator and I'll multiply my denominator, so that 8 is going to be distributed to each of my terms. So I'll have the limit as n approaches infinity of 12 plus 8 times 2n cubed is 16n cubed, plus 8 times 3n squared is 24n squared, plus 8 times n is 8n, and that's all over n cubed times 6, which is 6n cubed. Now I'm going to split up those fractions in order to simplify. So the limit as n approaches infinity of 12 plus 16n cubed over 6n cubed plus 24n squared over 6n cubed plus 8n over 6n cubed. Now my n cubed will cancel out with n cubed, and as n approaches infinity, because my highest degree in my numerator of my second term is smaller than the highest degree in the denominator, this term will go to 0. And again, looking at my third term from the fraction, because the highest degree in the numerator is smaller than the highest degree in the denominator, this will also approach 0. So I'm just looking at the limit of constants again. So it's going to be 12 plus 16 over 6, which I'll simplify to 12 plus, dividing each of those by 2, that's going to be 8 over 3. And then writing 12 in terms of 3, that's going to be 36 over 3 plus 8 over 3, which 36 plus 8 is 44. So my answer is 44 thirds for number 8. And 44 thirds is approximately 14 2/3 or 14.6 repeating. Now onto the second page. On the second page, it says for each problem, we're going to find the area under the curve over the given interval, and we're to set up our solution using limits as n goes to infinity of the upper sum. Now this sounds confusing, but there's an easy way to think of this. Remember from the previous worksheet when we found the area under the curve using those rectangles and the interval. Remember we had to calculate that change in interval and divide it by the number of rectangles we wanted. So if the starting value of our interval is a and the end value of our interval is b, the change in x is going to be equal to b minus a, but remember we're dividing that by the number of rectangles we're finding the area of, which in this case is n. So for number 9, we'll have 9 minus 0 over n, which equals 9 over n. Also, it's important to take into account the start of our interval. So x sub I is going to equal a plus I times delta x. So we know that our a value is 0, and we know that delta x is 9 over n. So x sub I equals 0 plus I times 9 over n, which is going to equal 9i over n. Now we're going to use each of these values in this next formula. This is the limit as n approaches infinity, because we're using the limit as n goes to infinity of that upper sum. So from the summation of, now as opposed to using k equals 1, I use the variable I. So we're going to go from I equals 1 to n of the function f of x sub I times delta x. So when we plug 1 in for I, we're taking x sub I, where I is 1, so that's 9 over n. So using this formula, delta x and x sub I, we can solve for the area under this curve. So let's get started. I'm going to have the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I. So we're taking x sub I, which is 9i over n, and plugging it in for x. So that's going to be 9i over n plus 5. And again, what I did, I took x sub I and plugged it in for x in the function. And that all gets multiplied by delta x, which is 9 over n. So what I'm going to do is I'm going to distribute my 9 over n to each of these terms, before I break up the summation. So I'm going to have the limit as n approaches infinity of the summation from I equals 1 to n of 9 times 9i, multiplying my numerators, which is 81i, over n times n, which is n squared, plus 9 times 5, which is 45, over n. Now I'll break up my summations. So I'll have the limit as n approaches infinity of, starting with that first summation, that's going to be 81 times I over n squared. And that will be added to the summation from I equals 1 to n of 45 over n. Now continuing, we'll have the limit as n approaches infinity of, I'll pull out that first term, which is 81 over n squared. So 81 over n squared times the summation of I equals 1 to n of I, plus, now we're taking the summation of a constant. So that's just going to be the constant times n. So 45 over n times n. Now continuing my work, we'll have the limit as n approaches infinity of 81 over n squared times, this was our formula. But as opposed to using k, we're now using I. But it's still going to be the same result. So that's n times n plus 1 over 2. That was our formula. And then we're adding 45 times n divided by n, which is simply 45. So I'll have the limit as n approaches infinity of 81 times n plus 1 all over, multiplying the denominator, n squared times 2, or 2n squared, plus 45. Now in my numerator, I'm going to need to distribute that 81n to n and to 1. So I'll have the limit as n approaches infinity of 81n squared plus 81n all over 2n squared plus 45. Now I'm going to split this fraction up in order to simplify. So I have the limit as n approaches infinity of 81 n squared over 2n squared plus 81n over 2n squared plus 45. Right away you can see that n squared cancels out with n squared, and because the highest degree in the numerator of this second term is smaller than the highest degree of the denominator, as n approaches 0, this term will go to 0. So now I'm just dealing with two constants. So that will be 81 over 2 plus 45. But I'm going to write 45 in terms of 2. So 2 times 45 is 90, and 90 over 2 is equal to 45. So I'll have 81 over 2 plus 90 over 2, which equals 171 over 2, which 85.5. So 172 over 2, or 85.5, is my solution for the area under the curve over the given interval 0 to 9. Now what we need to take from this is delta x, x sub I, and our formula. So let's continue on to number 10, remembering those. In number 10, delta x, remember, is b minus a over n, where a is the start of our interval, which is 0, and b is the end of our interval, which is 3. So I'm going to have 3 minus 0 over n, which equals 3 over n. Now, x sub I was the start of our interval plus I times delta x, which in this case is 0 plus I times 3 over n, which is equal to 3 times I over n. So we're going to be using 3 over n for delta x and 3i over n for x sub I. And we're plugging that into our formula. The limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I times delta x. So that's going to be the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I. I'm going to plug 3i over n into f of x. So f of x sub I, as opposed to having x squared, it's going to be 3i over n squared plus 3. So 3i over n squared plus 3, and this is all multiplied by delta x, which is 3 over n. So let's go ahead and zoom into our work and continue. So I'll have the limit as n approaches infinity of the summation from I equals 1 to n of 3i over n. If I distributed this square to both my terms, that's going to be 9i squared over n squared. Remembering laws of exponents. And I'm adding that to 3. And then in my next step, I'm going to be multiplying each of those by 3 over n. So now I'll have the limit as n approaches infinity of the summation from I equals 1 to n of 3n times 9i squared over n squared, which 9 times 3 is 27, so that's 27i squared over n cubed, because n squared times n is n cubed, plus 3 divided by n times 3 is going to be 9 over n. Now I'll separate my summations. So I'll have the limit as n approaches infinity of my first summation, the summation of I equals 1 to n, of 27i squared over n cubed. And I'm going to add that to the summation from I equals 1 to n of 9 over n. Now I'll simplify those by pulling out the constants. So I'll have the limit as n approaches infinity of, I'll pull out 27 over n cubed, so that will be 27 over n cubed times the summation from I equals 1 to n of I squared. And I'll be adding that to the summation of a constant. So that's going to be constant times n. So 9 over n times n. Now I'll simplify my second terms and apply the formula to my first term. So I'll have the limit as n approaches infinity of 27 over n cubed times, remembering the expanded formula of the summation for k squared, applying that to I squared, that's 2 times n cubed plus 3 times n squared plus n all over 6. And then I'm adding that to 9 times n over n, which my n's will cancel out and leave me with a positive 9. Now I'm going to simplify. So the limit as n approaches infinity of, so 27 and 6 are both divisible by 3. So when I multiply out my numerator and I multiply out my denominator, I'll be able to simplify those by dividing each by 3. So now I'm going to have 9 times 2n cubed plus 3n squared plus n, and that's going to be all over n cubed times 6 divided by 3 was 2. So that's 2n cubed. So again, what I did, I knew that 27 and 6 were both divisible by 3. 27 divided by 3 was this 9, and 6 divided by 3 was this 2. And that will get added to 9. Now I'll distribute that 9. The limit as n approaches infinity of, and as I distribute that 9, I'm also going to break my fraction up because they're all over the same denominator. So 9 times 2n cubed is going to be 18n cubed over 2n cubed. And I'll be adding that to 9 times 3n squared, which is 27n squared over 2n cubed. And then that will get added to 9 times n, which is 9n. And again, that's over 2n cubed. And then I'm finally adding that 9. So one more time, what I did, as I distributed my 9, I split up my fraction because each term was added together over that same denominator. And now I'll be able to simplify. N cubed divided by n cubed is 1. The degree of my numerator is smaller than my degree in my denominator, so that will go to 0 as n approaches infinity. For my next term, my degree in my numerator is smaller than my degree in my denominator, so that will also go towards 0 as n approaches infinity. So again, all I have are constants. So that's going to be 18 over 2 plus 9. And 18 divided by 2 is 9. And 9 plus 9 equals 18. So my solution for the last problem on this worksheet is 18. Now, if you're confused on any part, please feel free to leave your question in the comment below. I know this was a lot of information, and a lot of it was applying rules and formulas. So if you're confused on any of those or why we can use them, go to my website, maemap.com, maemap.com, and I'll get a tutorial video up for that. But if you're continuing on to the next worksheet, remember to like, subscribe, and share before moving on.